Hey guys, welcome back to AlgoYogi, and we are doing the trees series right now. So let's move on to our next problem, which is minimum time to collect all apples in a tree. Okay, so let's go through the description of the problem. We're given an undirected tree that has n vertices numbered from 0 to n minus 1, and these vertices have apples. Some of these vertices have apples. And we spend 1 second to walk over the edge of this tree. So walking from 0 to 1 takes 1 second. And the same applies basically walking backward. Now, what we need to do is return minimum time in seconds we're going to spend collecting all the apples starting vertex 0, and basically after collecting all the apples back to it. We need to return the number of seconds we're going to take, minimum time basically in seconds, that we're going to take to basically collect all the apples in our tree. Now, to know that if this one particular vertex contains apples, we are given has apple array that is basically of same size as n, and at index from 0 to n minus 1, so 0, 1, 2, 3, 4, 5, 6, for this particular example, we are given Boolean values, and those Boolean values represent if that particular vertex contains apples or not. So here we know, so index 0, 1, 2, 3, 4, 5, 6, we can say that index 5 is true, so 5 has apple, 4 is true, that has apple, and 2 is true, that has apple here. Now we need to collect these apples, and how are we going to do it? We're going to use the algorithm DFS, starting on index 0. So from 0 we're going to call DFS on its children. So we're going to make a call to 1 will make a call to 4, it will try to make calls, then it doesn't have any children, then it will basically we need to return some values. We need to have some base cases, and base cases are little tricky here. Now in our base case, basically if at a vertex, if I know it has apple, then I am going to return 2. Why 2? Because it will take me 1 second to come to this vertex from its parent, and also 1 second to go back. So that's why I'm returning 2 from here. Same will apply to basically here. So this will also return 2. And then now here is the thing. Now even if as a parent I do not have apples, but if I am receiving some apples from my children, then I have to pass those apples up, then I had to traverse this path, then I also have to add 2 here as well, walking this edge. If there were no apples in this path anywhere in this subtree or path, then I wouldn't add 2. However, like if I'm bringing non-zero value from my bottom, from my children, then I have to also add 2. So this will finally basically return 6 from here, from this this root. This subtree will return 6. And let's explore the other side here as well. This, we know this will definitely append 2, but let's go down because it has apple. So from this, walking over this edge will definitely have to add 2 as a value. But now it's going to explore its children, and exploring them is basically just not beneficial because we don't have any apples there, and that we will of course check using our array whenever we are traversing it. So then they will return 0, and this will add 2, and finally we will be returning 8 as an answer. I think that's the answer we have for our example. So it's quite really easy. It's just when we're calling DFS, first we will have to create an adjacency list using these edges. So basically having this parent-child relationship, or we can call it neighbors relationship. It's like we'll be creating adjacency list and have these neighbors connecting with each other, so that later we can start with index 0 and then traverse all the children of 0, and those children can call their children in DFS. So let's try to implement the solution. Okay, so let's code our solution here, and as I said, we need to create this trees adjacency list of each vertices and their neighbors. So we're going to call it, let's call it tree adjacency list, and that's initially will be empty. So every vertex and empty array like as neighbor, and that will be for I in range n. Now let's fill it up for, let's call it v1 v2, basically vertex 1 vertex 2 in edges, and that would be basically we're going to put it into our adjacency list. So v1 will have v2 as neighbor, and v2 will have v1 as neighbor. v1 as neighbor. Now we're gonna have a DFS function. Let's call it the DFS that will have current node that I'm exploring and its parent, because we're going to have basically in our adjacency list one vertex is the neighbor of another vertex as well, so they will both make call to each other, and we don't want to get stuck in the loop. So if parent is equal to child, then we will basically have that case where we just disregard that and return the call back. So let's have time variable like just 0, and let's make call to child of our current node's children, and here is when we check if child is equal to parent, right? Then we just continue. We're not gonna call the DFS function on this one, so we'll just say continue. Otherwise we're gonna get child time from using DFS on this child and providing current as its parent. Okay, now if child time returns something, basically if there is some child time is being returned, that means we need to basically add 2 to our returning time from here. So if child time or has apple at my current vertex, in both cases I will basically add 2 to my main time. So time will basically be 2 plus child time here. So child time can either bring 0, as we have seen in the explanation in the conceptual part, or has apple's index is true. In both cases we are appending 2 while returning the value. And finally let's just return time, and in the end we can make the call to our DFS on index 0, that's our starting vertex, and for its parent we can just provide -1. Doesn't really matter, and try to run this. Invalid syntax for child in our tree adjacency list, and this is returning. Yes, the condition is basically for the children, for the child. If child basically has any basically has the apple, because this child time is coming from that child's children, so that was a little confusing here. But anyway, like let's try to run it now, and yes, let's submit. Okay, awesome. Okay, let's write down the time complexity for this. Time complexity is going to be big of n, where n is the number of vertex, and because we're visiting each vertex one time or maybe 2 times, but doesn't really matter. That's same. Space complexity will be big of n square, and that's because for each vertex we are storing, no, I think it's also going to be n, because in our adjacency list, that's where our all the storing is happening, and we have all the vertex and their neighbors, so that's it. So 2n I would say, but n. So let's go back to our AlgoYogi and mark this problem solved. If you guys are using AlgoYogi, then you'll have the solution over here, so I'll upload it right at this place. So see you guys later. Bye bye. See you in the next problem.